Hello and welcome to part 6 of the video series about feature engineering, dimensionality reduction, feature selection, and feature extraction. In the previous part of this video series, we discussed basically the derivation of principal component analysis, which is the most famous feature extraction method. Although there are others, but PCA has a lot of theoretical as well as practical properties. And we went through the mathematical derivation, not in a huge detail, but very briefly by skipping certain steps. But we went through the derivation, then it turns out that the principal component analysis, it basically relies on eigen decomposition of a covariance matrix. In this particular video, we will actually be implementing principal component analysis in Python using NumPy. Although the PCA function is available in scikit-learn, you can use that one. But we are going to implement a PCA function from scratch completely in NumPy. So let's dive in and go to Jupyter and implement PCA. So for that, we need some of the packages that we need to import. For example, we need NumPy as NP. We also need linear algebra library. So import from NumPy, import linear algebra as, let's say, LA. We need that. We also need maybe we need matplotlib for certain plottings. Matplotlib.pyplot as plt. And then let's use a phase data set to work with. So let's import from sklearn dot datasets. Import, let's say, fetch LFW LFW people. Yeah, so import this one. So let's see if all the imports they work. Yeah, they're working very well. Let's import the data. For example, faces is fetch LFW people with minimum faces per person equals to, let's say, 80. So fetch all the data in which the minimum faces per person is equal to 80. So let's see, it is fetching that data. Let's see how long it goes. Yeah, it is there. So now it has faces. So let me show you the dimensions of a particular face. Let's say, let me show you a face, for example, plt.imshow faces.images, let's say 0. Let's say we use the certain color map. Let's say C map is equal to bone. Let's say that. So that's an image. That's the image. Yeah. So further, if you really see, that's the first image, index at 0. There are other images. Let's see the dimensions of the data. So for example, faces dot images 0 dot shape, that is what is the faces, I guess, yes, faces. So basically each image is basically a 62 by 47 matrix, which means the total number of dimensions or the total number of pixels, they are 62, static 47. So the total number of pixels are 2914. So the dimensionality of the data, if we just flatten that image out, the dimensionality of the data is 2914. So basically each of these faces, there are several faces, each of these faces is a point in 2914 dimensional feature space. So the dimensionality of the feature space is really high, as it is around 3000 dimensions in this particular case. We also have, in this particular structure, we also have data in flattened form. So let's read that data. Faces dot data dot transpose. That's our data. If you see x dot shape, so we have we have exactly 1140 faces or samples. That's the value of n, and that's the value of d, the dimensions of the data. Now what we really do is, according to the derivation of PCA, we first compute the mean vector of the data. Let's say the mean vector is x dot mean x is equals to 1, and we also do that np dot new x's. So that's mean. So let's check the shape of the mean, m dot shape. So the shape of, so that's the mean vector. This command np dot new x's, it actually adds this dimension. Otherwise it would have been 2914 comma nothing, and sometimes that has problems in broadcasting. So it is always good to, not always, it is mostly good to add these dimension explicitly. So that's the mean vector. By the way, why don't we see the mean vector? Mean vector at the end of the day is also a face. It's a mean face. So let's see how the mean face looks like. Why not? Let's play with that. Oh, Control V. Let's see the mean face, how it looks like. So it is basically mean face, which is m dot reshape to 62 by 47, I guess. Yes, 47. So reshape into that and then just show it. So it should be a face at the end of the day. So how will it look like? Oh, that's the horrible. That's the mean face. That's the average face. In fact, what we have done is we have computed the average value or the average face. That face was 2914 dimensional point. We can reshape that into a matrix, and then we can view that matrix as an image. And here is the mean face as an image. Okay, next, we have our mean face, we have our x. Let's compute the centered matrix, which is xc, that is x minus the mean. And then we can compute our covariance matrix, which is simply xc dot xc transpose. That's our covariance matrix. So if you see the shape of covariance matrix, that should be d by d. Yeah, so that is 2914 by 2914 matrix. So next, what we have to do is we need to compute the eigenvalues and eigenvectors of this this C, the covariance matrix. So eigen decomposition. So linear algebra library has this eig function to do that. Although there are smarter functions, SVD and stuff like so, but because we haven't dealt with those kind of functions in theory, so let's rely simply on eig function. So let's see what we, it returns the eigenvalues, let's say E, and eigenvectors, let's say W. So that is L, A, let me keep that as capital W. These are our vectors, LA dot eig, and here we give C. Yeah. So it will take some time, so bear with me because that's a large matrix. 2914 by 2914, it's a large matrix. Computation of eigenvalues is not a simple process. It takes some time, so it is going to take some time. So hold on with me and let's see how long it takes to compute this particular result. So yeah, so E will contain all the eigenvalues. E will be an array. W will be a two-dimensional array or a matrix. So yes, it returns. So let's see E and W. By the way, it is no guarantee always that the E, the eigenvalues, they are sorted and the W are sorted. There is no such guarantee. So what we always should do is to sort them, because the highest eigenvalue, the corresponding eigenvector to that, is the most important dimension. So the dimensions are selected based on the values of, or the magnitude of the eigenvalues. So let's sort the eigenvalues in descending order, because the highest eigenvalue, the eigenvector corresponding to that, is most important. So let's see, how can we sort IDX? For example, is np.argsort E, and let's say I want to do that in descending order. So I do this, so that's the index in descending order. So E sorted is simply E IDX, and not only that, W sorted is W IDX. So yeah, so now we have the first W is the most important, the second W is then the next most important, and so on. Let's see the distribution of this E, how this E is distributed. So let's see that plt dot plot np dot range length of E, and then we can have this E. So let's see how the plot looks like. That says that this E decays very quickly. I mean, the first few vectors, they are very important, and then all the vectors, the rest of the vectors, they can simply be reduced. So yeah, so let's for example try out. Remember our D was initially 2914. Let's just reduce that dimension to 100 dimensions. Let's say our K is, let's say, 100. Let's reduce the dimensions to 100, which means W K is simply W, and it is from 0 to K. So pick all the vectors from 0 to K. So that's our WK, let's say. Now if you see WK, the dimensions or the shape of that is basically D by K. Yeah. So what we do next is we transform our data to Y, and let's see how the Y looks like. So Y is basically WK transpose dot XC. So that's our Y. If you see Y dot shape, so now the data is basically 100-dimensional data. So from 2910 dimensions, we actually moved to 100 dimensions. Not only that, we can reconstruct our data back using this Y. So let's reconstruct our data and see the reconstruction from this 100 dimensions and the original data, how that looks like. Just visual inspection. So let's reconstruct our data. So let's say XC reconstructed. XC reconstructed is simply WK dot Y. So that is XC reconstructed. If we see XC reconstructed dot shape, it is again 2914 by that. Not only that, to reconstruct it fully, we have to add the mean value also. So X reconstructed is XC, remember, we have subtracted this mean. So if we add the mean again, we have our X reconstructed back. Now if you visualize the reconstructed X and for example the first value of the first phase after reconstruction and the first phase that was original, let's compare them because we have reduced the dimensionality significantly. So let's see how these 100 dimensions, how much information it kept to reconstruct the original data. So let's say plt dot imshow X original. Let me pick the 0th phase, the very first phase, and let's say CMAP is bone. That's the bone. That's our yeah, that's the original phase. What's the problem here? Oh, I have to reshape that. Reshape that to 62 to 47 because otherwise it is no longer a matrix. So yeah, so that's the original phase. See that? That's the original phase. Now I'm going to show you the reconstructed phase out of just 100 dimensions. So yeah, let's see. So the decision would be yours. Reconstructed. So that's the reconstructed phase. Yeah. This is the phase that is reconstructed after reducing to 100 dimensions. And this is the face that is the original. Yeah, can you see that? Maybe we can increase the dimensions from 100 to more dimensions, and this looks like more similar. So for example, let's go and pick this k as, let's say, 1000 rather than 100. Let's pick them as 1000. So let's see, it's 1000 now. Let's do that. It is 1000. It's 1000. It is this. That's the original. That's the original. And now we are going to reconstruct our, yeah. So as you can see, the dimensions of the subspace, as you increase that, the similarity becomes high. Yeah. So it is important to note what should be the best value of k, what should be the best value of the subspace, what should be the dimension of the subspace. There are ways to compute the good values for k. For example, there are energy values to compute. For example, how many eigenvalues you keep to keep the total 95%, if you want to keep 95% of information or 96% of information, and so on. So there are ways to actually compute good values of this k, but here I'm showing you that even if you reduce, for example, from 3000 to just 1000, you are very, very good. You see that? In fact, it is almost identical. Maybe that work on just 500. Maybe we can see the result on 500, although there are good ways to compute this k, but let's see on 500 what happens. So this is the original face and this is the reconstructed face. As you can see, even on 500 dimensions from 3000, the reconstruction is beautiful. Now I turn to visualize this W. What are these W's? You might have heard a term eigenface. So let me show you this eigenface. Basically, let me show you a few of those. So figure axis as plt dot subplots. Let's have 2 by 4. Let's see the first 8 of them. And for idx, ax idx, enumerate ax dot flat, ax idx dot imshow, wk idx dot reshape into the matrix 47, and then set the color map as bone. Maybe I need to off these x sticks. idx dot ax idx dot set, x ticks nothing, y ticks nothing, empty. So yeah, let's see. Oh, what happens? idx enumerate ax dot flat. What's the problem here? Name enumerate is, oh, I have misspelled something. Enumerate, it should be enumerate. Yeah. So here these are called eigenfaces. This is the first axis of the subspace. This is the second axis of the subspace. This is the third axis of the subspace. This is the fourth axis of the subspace, and so on. What is happening basically is, if, for example, if the value of k is, just assume the value of k is 8. That means all the faces in this data set, they can be constructed using these 8 faces. Some portion of this axis plus some portion of this axis plus some portion of this axis plus some portion of this axis. And if you have different coefficients using the same basis, you can construct different kind of faces. And that was the concept introduced earlier by Turk and Pentland, and it was become really iconic, named eigenfaces at that time. It is just the eigenvectors of the covariance matrix of the phase data set. There are Fisher phases as well, that is Fisher decomposition, linear discriminant analysis, Fisher linear discriminant analysis, that also became iconic Fisher phases. That is a different kind of dimensionality reduction technique, but I just wanted to show that each of these W, that is actually is an axis, and here in the phase space the x's are also the phase axis, different components of axis. For example, if you see this particular axis, it highlights the eyes and lips and some portion of nose. So it has this particular contribution. If you see, for example, this particular phase, the contribution is the bright area. In this case, the contribution is the left area mostly. In this case, the contribution is the right area somewhat. And similarly, if you see in this phase, the contribution, the axis that is contributing is normally this area and this particular area and so on. It is important also that all these faces, although they look like, they may look like to you, or they are all faces, they are orthogonal, which means as a vector, if you take dot product of this and that, that is 0, the dot product of this and that, that is 0, and so on. Yeah, so that is also there. So that's about the PCA, principal component analysis, the implementation of it. I've done this implementation particularly on phase data, but that can be done on any kind of data. I have not told you the good ways of selecting K, although they are there. So for more information and for more fascinating kind of implementation and derivations and more insights, I would recommend you to enroll our course on AI Sciences, that is full course on dimensionality reduction. There we discussed not just PCA, we discussed a lot of other dimensionality reduction techniques as well. So yeah, hope to see you in the course.